Alright, here we are in section 3D. We're going to finally wrap up the last section of chapter 3. We've been talking all about measurements and we've done a lot of math work, and we have some final concepts to talk about, and that is, how do we measure matter? And there are four main ideas we're going to talk about in this section: measuring matter by weight, mass, volume, and then density. So your book opens up this section talking about an everyday, ordinary block of gold. I don't know about you, but I would love for blocks of gold to be everyday and ordinary in my life. But anyway, so it opens up talking about how you might discuss the matter inside of this block of gold. And so there's several words I'm sure you've seen before: weight, mass, volume, density. Okay, those are all things you should be familiar with from other classes. They also mention counting the number of atoms. So it's really important to note all of this is quantitative, meaning numerical information: weight, mass, volume, density, number of atoms. All of that is quantitative, but only these first four, weight, mass, volume, and density, involve measurement. Counting the number of atoms would be something you would do that's counting. It's still quantitative, but it's not measurement. So we can talk about how much matter in two relative terms, and these are related but different. So let's talk about each of them. So weight. So that's what most people are usually concerned with. You know, when they're going to step on the scale in the morning, they're not like, oh, I have too much mass. Okay, usually it's I weigh too much. So, or I weigh not enough. Also problems for some folks. So, anyway, weight has to do with the force of gravity on an object. Okay, so gravity exists between every single object in the world. Okay, you know, between me and my computer right now, there's some force of gravity pulling us together. But because we're both, you know, neither me or my computer are the size of the Earth, okay, the gravity is fairly small. But since the Earth is so large, okay, the pull that it has on us is fairly large compared to our pull on it. So weight measures that pull. It is a force, and forces are measured in newtons. Okay, if you remember, we've talked about derived units. Newtons are a derived unit made up of kilograms times meters per second squared. Okay, so the weight of something depends on Earth, meaning it depends on where you are on Earth, actually. It varies slightly. And then if you were not on Earth, your weight would not be the same. Okay, we use a couple instruments to measure weight. One is a spring scale, which I'll show you in class. Basically, it's a spring that gets pulled down, and depending on how far it gets pulled down, we know what the weight of the object is. The other is an electronic scale. Okay, the important word to know here is scale. Okay, so when we're measuring weight, we use a scale. All right, in contrast, let's talk about mass. Okay, mass is measured using a balance. So we might use a regular old analog balance like we have in our classroom, or there are also really nice, more sophisticated electronic balances. Okay, but remember, we use a scale to measure weight and a balance to measure mass. So what is mass? Mass has to do not with the force of gravity, but with how much matter something contains. Now, they are related because the more mass, the more gravity, okay? But they are distinctly different, okay? So rather than using newtons to measure weight, we use kilograms. And the mass of something is going to be the same no matter where you are. So even if you leave Earth, you're still going to have the same mass, even though your weight will change. So here's a nice diagram that kind of shows this. So if we've got an astronaut, that astronaut has a mass of 120 kilograms while he's on Earth or she's on Earth. Weight can be approximated on Earth by multiplying your mass by about 10. It's really about 9.8, but we'll round it up to 10. So if you take the mass in kilograms and multiply by 10, you get the approximate weight 1,200 newtons on Earth. But then look at what happens when he goes to the moon. His mass is the same, but his weight is different, okay? So if you compare those two, the force of gravity on the moon is about 6 times smaller than that of the Earth. So we divide the weight by 6, we get the approximate weight on the moon. So he weighs a lot less. It's like going on a diet, and you don't even have to change what you're eating. It's pretty nice. So comparing those two, again, weight has to do with force of gravity. Mass is amount of matter. Weight is measured in newtons, while mass is measured in kilograms. Weight depends on where you are. Mass is the same everywhere. It doesn't depend on where you are. We use scales to measure weight and balances to measure mass. Okay. Your book makes this statement: equal masses weigh the same at a given location on Earth. I want you to sort of break that down. Equal masses. So if two things, the weight of A, whatever that is, and the weight of B are the same, then their masses will also be the same. But that does not mean weight equals mass, okay? So they're related, okay? If weights are the same, then masses are the same, but they're not the same thing, okay? That's an important distinction. So I'm going to ask you two questions that I hope puzzle you. All right, the first one: what is heavier, a pound of gold or a pound of feathers? Think about it. When I say heavier, that means which one weighs more, a pound of gold or a pound of feathers? And you probably heard this question before, okay? And the answer lies in this word, a pound. Well, what is a pound? A pound is a measurement of weight, okay? It doesn't matter if the pound is of gold or of feathers. A pound is a pound. So which is heavier? Neither. They're both the same, right? They're both a pound, okay? All right, so now's the follow-up question that you're going to have to think a little bit harder about, because you might have heard that riddle before. But what about this one? Which has more mass? A pound of gold or a pound of feathers? I'll let you think about it for a second. All right, so we determined before that a pound of gold and a pound of feathers have the same weight. So what can we say about their masses? Well, that comes back to this statement. Again, equal masses weigh the same. So if two things weigh the same, what can you say about their masses? That's right, they're equal. So which has more mass, a pound of gold or a pound of feathers? Again, the answer is neither. All right, they both will have the same mass. Now, will their mass equal the weight? No. Mass and weight are different things, but both this pound and this pound, they weigh the same. That means they have the same masses. All right, another way we can talk about how much of something we have is volume. Typically, this is more useful for liquids or granular substances, but sometimes we find the volume of solid objects as well, and we have some nice formulas for a few solid objects. You can find this in your textbook. Of course, any kind of rectangular solid, it's just going to be length times width times height is your volume, okay? A cube, is the same, length times width times height, but since all of those are the same, we might call it side cubed. So S times S times S, all right, side cubed. And then there's several others. Quickly, a sphere is 4 pi r cubed. 4/3 pi r cubed. And then a cylinder, 2 pi r squared h. One important question I want you to think about is, how many spatial dimensions will a volume always have? What do I mean by spatial? All right, not terrestrial, okay, spatial. Spatial means having to do with space. Well, think about it. How many dimensions do the things exist in? 3, right? 3 spatial dimensions. So a volume will always be something cubed, okay? So here's another important idea to think about, okay? 1 meter cubed will be equal to how many centimeters cubed? I want you to answer that question for me. by posting it as your response to this assignment. This is the question I want you to answer. And you don't have to be right. We're going to talk about this a little bit more in class. I want you to take a guess. You know that 1 meter equals 100 centimeters, but what is 1 meter cubed in centimeters? Think about that. When we measure volume, there's two different ways we might use, and we're actually going to do this in class. The first way is a direct measurement. Well, I'm sorry, the first way is not either of these. The first way would be to measure using a ruler and then use a formula from that diagram we just saw with all the different geometric shapes. But if something is not nicely shaped, if it's irregular, and if it's a liquid or granular solid, we'll just pour it into something we call a graduated cylinder, okay? It forms this sort of curve at the top. We call it a meniscus. And we measure at the bottom of the meniscus where that bottom of the meniscus hits. So in this case, it would be 4.123.4, and it's right on the line, so we estimate one more digit. So this would be 4.40. I'm going to guess these are milliliters. So 4.40 milliliters of water. Okay, so that's pretty easy and direct using a graduated cylinder. But if we have a solid object that's irregular, meaning not a cube, not a sphere, we can use water, okay, to help us measure the volume. So here's our dinosaur guy. We measure how much water we start with, and then we put our dinosaur guy in. And what we find out, and you might have found this out if you've ever taken a bath before, is that when you put something in water, it displaces the water. So it makes the water level rise. So in this case, now the new water level is 5.123, and it's right on the line, so 5.30 milliliters. So the difference then between where the water started and ended, that's the volume of my dinosaur guy. So in this case, it would be 0.40 milliliters. Okay, so that's what we call the water displacement method for finding volume. Now, that's really useful for some things. Obviously, we know that we could only use that water displacement method if the thing we're trying to measure the volume of will sink. Okay, if it will sink. Now, what determines whether something sinks or floats in water? Okay, it's not just the mass, it's not the weight, it's not the volume, it's this other idea, this something called density. Density has to do with how much mass you have in a given volume. And density is really useful. Different things have different densities. So if you layer different liquids in the same cup, you'll notice that the ones with the highest density that are have the most stuff in a given volume will sink to the bottom, and ones with lower densities will float on top. All right, and when we measure densities of liquids, we usually use the units gram per milliliter, while with solids we usually use grams per cubic centimeter or centimeter cubed. Both are totally acceptable and interchangeable. Okay, so density has to do with how much mass is in a volume. So the formula for density is mass divided by volume. Okay, mass divided by volume. All right, that wraps up 3D about how we can measure matter. I hope you sort of felt like this was informative. Definitely give me feedback, let me know. If I went too fast, too slow, if you have any questions, please definitely ask them in class. And we'll do some practice on math problems involving density especially, because that's something you will see in the future. Alrighty, that's it.